Hello everyone. In the previous lecture, we had started our discussion on the important topic of shear center, and in that lecture, we had first of all motivated uh, the discussion of shear center by referring back to the preliminary considerations of bending uh, in conjunction with the possibility of twisting. And then we had discussed a few important points uh, which uh, which related to the physical considerations associated with shear center. At the very end of that lecture, we had also mentioned that for the actual derivation of the formula that we need to use to find out the shear center, uh, one important assumption that we have to make use of is that the cross section will have to be made up of very thin members. Now, in addition to that, what we'll also need is that the cross sections will have to be of an open nature. So the cross sections that we'll be considering will be thin walled open sections, and as I had mentioned in the previous lecture, this has direct importance, immediate relevance for structural mechanics, because many of the cross sections like the Z section, the L section, the T section, the I section, they're all exactly like that. They are thin walled, and they also have an open structural form. So because we want to have a general derivation of the formula, what we'll do is instead of considering each individual case, we will consider a generic thin walled open section in this lecture. So the kind of beam that we are going to consider is will have a shape somewhat like this. So I'd like to mention that this beam has a thin walled open section, meaning that this particular thickness here, it is it's very small. This thickness is very small, and because this end is not joined to this end, unlike for example an annular circular cross section, so because this is not joined to this, this is an open section. What we'll also consider to concretize our ideas is that this beam, just like in the previous lecture, would be attached or fixed to a wall here at this left end. So it will be something like this. We will set up our coordinate axis in this fashion. So this will be our x-axis. This will be our y-axis, and this will be our z-axis. Now, a word of note about the x-axis. In general, it is not necessary for our x-axis to pass through the centroid. So for most of the discussion that we would be having, it is not at all necessary that the x-axis passes through the centroid of this cross section, but it just so happens that near the end of this derivation we'd be using the formula for the bending stresses that we had developed in during our discussions of unsymmetric bending. And please remember that there we had actually considered the y-axis and the z-axis to be centroidal axis. And if the y-axis and the z-axis are centroidal axis, when we are using the formula for the bending stresses, so it necessarily follows that if we have to again use the formula for the bending stress or anything that has to do with the mathematical derivation of the unsymmetrical bending, then it is also necessary that the x-axis has to pass through the centroid. So you have to remember that. But for most of the discussion, we don't require the x-axis to be the centroidal axis. Okay. Now, what we'll do is we'll apply a load. We will apply a load like this. Please note that this load, this load is in the form of a transverse force, and the line of action of this transverse force is situated at a distance of which will be denoted by the letter E from the x-axis. So what I mean to say is that this distance that will be E. Now, because we want to develop this entire mathematical derivation for the shear center, what we are going to say is that this force, this externally applied transverse force, is going to pass through the shear center. So the shear center will lie somewhere on this line of action, and only when that happens we can rest assured that that this distance E will tell us, will give us an estimate of where the shear center is located. Now one may think immediately that we are only considering a transverse force which is parallel to the y-axis, but you please note that there is no restriction about this about the choice of this y-axis and the z-axis, other than the fact that for the requirements of a derivation they have to pass through the centroid. So if, for example, if we have a force which is not oriented in this fashion, rather maybe somewhat oblique like this, then there is nothing stopping us from taking a y-axis which is parallel to that orientation. So that kind of an oblique orientation. So we can very well take the y-axis to be oblique like that and parallel to this thing. So whatever we derive here will absolutely hold true. Okay. Now, what we are going to do is will be exactly like the case of the general cross section that we considered earlier. So what we did earlier, so let's take a quick look here. We had taken a cut section, considered this kind of a cross section, which exposed this kind of a cross section, and then we considered the cut piece which came out in front of that cutting plane. So we considered this piece, and we considered that if the transverse force is passing through the shear center, then the net torsional moment due to this transverse force and that contributed by the distribution of shear stresses here would be equal to 0. So the torsional moment from this would be balancing the torsional moment of this, if that balance will be true only if this passes through the shear center. And now in the present case, since we are already saying that this passes through the shear center, so if we take a cut section somewhere here, then the distribution of shear stresses there in the exposed surface there would be balancing the torsional moment here. Okay, so let's draw the cutting plane here. This drawing is going to get a little bit cluttered, but we'll have to deal with it. So So let me draw this other line also. That will be touching here and going all the way around. Be having it here, and so let me clean that up a little bit. Okay, so that is the section which will be exposed by this orange colored cutting plane. Now, as we had done earlier, what we are going to do is we are going to take out this cut piece. So what I'll do very quickly is to name the piece which is in front of the cutting plane as 1 and the piece which is behind it as 2. So this 1 represents this entire piece which is in front of the cutting plane, and the 2 represents whatever is behind it. And we are going to consider this cut piece 1. Okay, so let's go to the new page and draw that again very quickly. So we have a So this is our cut piece 1, and this hatched portion that will represent the section over which we are going to have the distribution of shear stresses that is pertinent to our discussion. Okay. Let us not forget that we have our transverse force acting like this. All right. So I repeat again that it is the distribution of shear stresses which is present over this hatched part which will contribute to a torsional moment which will exactly balance the torsional moment that is contributed by this transverse externally applied force when we take the moment about the axis, and that axis would be this x-axis. Okay, so let me make that very clear here, that we are still considering this as our distance E. Now let us remind ourselves that the whole motivation of considering such a special kind of cross section, namely a thin walled open cross section, was to make the determination of the shear stresses relatively easier. And the easy part here has to actually do with the thinness, primarily with the thinness of this section, because you understand that because this is such a thin section, there would not be any appreciable distribution or variation of shear stresses across this thickness. So across this thickness or across this thickness, there would not be any appreciable variation of the shear stresses. Okay, now what we are going to do to actually obtain some expression of the shear stress is we are going to consider a little element cut out in turn from this cut piece. So the little piece that we are going to consider would be something like this. So this is the piece marked out by the white border that we are going to consider. So if we isolate this piece out, it is going to look somewhat like this. Okay, now what we are going to do is consider another coordinate axis which would be fitted along with or along this cross section. So what I mean to say is that I want to set up a curved axis which is like this. So this will be represented by S. Please note that my X is still oriented like this. My Y and Z axis are very much like this, but they are no longer under consideration. Now I need to simplify the consideration of this picture here a little bit, and for that I will change the way that I am viewing this. And this is a crucial step and this will considerably simplify our subsequent discussion. So what I'm imagining is that I'm looking down. I'm looking down. So I'll draw an eye here, just like our high school science books. So this is our eye, and we are looking down. So okay, so this is an eye. This is the okay. So we are looking down on this. So if we look down on this, what will it look like? This little stress element that I have drawn here, what is it going to look like? Well, let's see. So from here, I'm going to obtain this. Please note that this is a top-down view. Note here that the S-axis, it is in this direction, and the X is in this direction. Now let us not forget that our primary objective here is to find out the distribution of stresses on this part here. So in this diagram, that corresponds to this little part here. And that edge, it corresponds to this edge. So I repeat, this edge here in this diagram, it corresponds to this edge here, and of course this edge, this top edge along which the S is oriented, that is this edge. All right. Now because our primary objective is to find out the distribution of the shear stresses, let us go back to our ideas of undergraduate mechanics and try to depict the distribution of the stresses over all these edges. So what we are going to do is to keep this picture relevant, like immediately relevant for our subsequent derivation. We are going to consider only those stress components on this stress element which are oriented along the x direction. I repeat, we are only going to depict those stress components which are oriented along the x-axis. So you understand that this will be sigma xx these two vertical shear stress components will be related to the sigma sx. So but this one will be sigma xx plus del sigma xx del x delta x. So note that what we are doing here is we are considering that this length is delta x. Consequently, if we go back to the previous diagram here, this length is delta x. And you also note that this distance is, or this length is delta s. Consequently, just like we have depicted the sigma xx through an increment of del sigma xx del x delta x, here we are going to represent this vertical shear stress component through sigma sx plus del sigma sx del s, because now we are moving along the s direction, times delta s. So please note what is the underlying idea here. Why are we doing all this? We are doing all this because our ultimate aim is to find out an expression for sigma sx. So we can do that if we can express somehow the sigma sx in terms of the sigma xx, because in our previous lectures we have already developed expressions for sigma xx under a general case of unsymmetrical bending. So even if we have a very general cross section, we can and a very general kind of loading, we know how to write down the expression for sigma xx in terms of the given moments, which is the externally applied load, and if we can do that and somehow we can relate the sigma sx to the sigma xx, then our job is the first step of our job towards finding the shear center is done. And this is, mind you, the most complicated step of actually finding out the sigma sx. Okay. With that idea, what we can immediately do is to write down the force equilibrium along the x direction. Before we proceed, it is extremely important to note that if we consider this diagram to be like a free body diagram for this stress element, and when I say free body diagram, I basically mean that each of these stress components would be multiplied by their corresponding cross sections. So in that case, if we were to consider those corresponding forces, then this diagram in terms of a free body diagram is certainly not a complete free body diagram. So let me write that down. This is not a complete free body diagram, because you note that we have only depicted the stress components along the x direction, because that is what we are going to do. We are going to write down the force equilibrium equation along the x direction, but in reality there would be other stress components along these various edges. We're just not depicting them. So what we are going to do is we are going to consider all of these stress components, multiply them by the corresponding areas to obtain the forces, and then set them equal to 0. So the summation of them to be equal to 0. So for force equilibrium, along x direction. Now I realize it's not the most convenient configuration here to switch between the previous page and the present page, but I am limited by space here, so sorry about that. So the first thing that we're going to consider is this one, the sigma xx over this face. So you understand that this face has a thickness of t. You note that this face again is corresponding to this one, which has a thickness of t, and it has a length of delta s. So sigma xx times t times delta s with a minus sign in front, because we are taking the force equilibrium along the x direction, meaning the positive x direction, and this thing is you note here is oriented along the negative x direction. So the next thing that we are going to write is the contribution to the force due to this, and that will be plus, because it is oriented along the positive x direction, sigma xx plus del sigma x, del sigma xx del x delta x times t delta s. And next, considering this stress component, this shear stress component sigma sx, what we will obtain is minus sigma sx times t times delta x. The minus sign is coming because if we just quickly refer back to the previous page, you see that the sigma sx is oriented, this sigma sx is oriented along the negative x direction. Next, considering this contribution, which you note is oriented along the positive x direction, we'll have sigma sx plus del sigma sx del s delta s, this whole thing times t into delta x, and this entire thing has to be equal to 0 because the stress element is understood to be in static equilibrium. Now when we are writing this, you note one important thing. We are assuming that the thickness t is not varying along the s direction. So what I mean to say is that if you move along this, in general the t can vary. If it varies, then what we have to do is we have to take this contribution of t inside here with the sigma sx, because you understand that if t varies with s, then it will be sitting inside this delta, the derivative with respect to s. But here we are not considering that extra complication. We are just going to write it out like this. So from this, what we can obtain is that okay. Now see, as far as our goal of expressing the sigma sx, in terms of the sigma xx is concerned, which we understand to be something that we know. We are almost done. So how can you actually find it out? So what we'll do is we'll transpose the sigma xx term to the right hand side, and we will integrate. So you understand that this t cancels, and we are going to transpose this to the right hand side, and then we will integrate both sides with respect to s. So what that will give us is sigma sx is equal to minus integration del sigma xx del x ds. Now you see what we have written here is far from complete, because it is absolutely possible to write this in the form of an indefinite integration. But if we do that, what we are basically doing is, as we have written it here, we are missing a constant of integration, because on the left hand side we have integrated with respect to s and we have gotten rid of this derivative, but on the right hand side we are doing this, we are getting this. But when you do this kind of an indefinite integration, we are actually left with a constant of integration. So if we don't write that, it is going to be wrong. But what we can do alternatively is we can consider this integration to be done from the point s equal to 0 to the point s equal to s. I repeat, we can consider that we are doing this integration from s equal to 0. So let me write that down. We're doing the integration from 0 to the generic point s. Now, if we do this, you have to understand that what we are basically doing here is, so I have to erase this left hand side and rewrite that again properly like this. We have obtained the sigma sx at the generic point s minus the sigma sx at 0. All right, so what's going on here? You see, we can just quickly refer back to this diagram here. You see, we are starting our s axis like this, which means the starting point is somewhere here. This is one end of the open walled cross section. So this is the part where s is equal to 0. So this is where s is equal to 0 here. Now you note that we are writing the expression for the sigma sx. So correspondingly this is also s equal to 0, and we are proceeding like this. The whatever we have obtained here, like sigma sx evaluated at 0, basically means the value of the sigma sx which is present here. But that is an open section, is an open end, and because that is an open end, you note that that value has to be equal to 0 there. So so if we go back to our derivation here, what we are going to obtain is that this term is going to be equal to 0, and what we will be left with is just the expression for sigma sx, and we are not going to write this vertical line with a subscript s to denote that this is sigma sx evaluated at any s. rather we'll just keep it simply like this, with the understanding that this is evaluated, that the left hand side, this term is evaluated at some generic S, and the right hand term will be exactly remain as it is. Now, because we have written all of these things, especially that sigma Sx is equal to 0, and we, if we go back to the previous page, we'll see that we have isolated our little stress element from here, and we have said that this sigma Sx is equal to 0. But you note that if that sigma Sx is equal to 0, so if that sigma Sx is equal to 0, then why are we not writing this this sigma Sx is equal to 0? Because you note that the edge that we are depicting here, so this edge is this edge. I repeat, this edge is this edge. So we should have written this sigma Sx to be equal to 0. But you note that this stress element has been drawn in this fashion only as a special case. What ideally we should have done is to consider a stress element which was not starting from this open end, rather it was starting from somewhere in the middle. In that case, this S would not have been at S equal to 0. It is important to have this much understanding when you are looking at this derivation. It is also important to note that if we are actually writing our sigma Sx for this particular edge, does it really answer our objective of finding out the stress distribution here? Because I've already mentioned that we are kind of happy that we have found out sigma Sx in terms of the sigma Xx in terms of the integration, but does it really answer our objective? The answer is yes, it does, because you note that here on this edge at S equal to 0, this one, this is our sigma Sx. But on this hatched part, that would be actually sigma Xs. So if we were to actually write down, let me write that down in red just to just as a special case. So our this red colored thing, stress component, would be sigma Xs. But we note that sigma Xs will be equal to sigma Sx, and it is based on this fact that we are kind of happy that we have found out this expression for sigma Sx. Okay, so this is like an indirect way of being happy. So since we have managed to find out an expression for sigma Sx, we have also managed to find out an expression for sigma Xx. It is exactly the same thing, but that entire thing is now expressed in terms of sigma Xx. So our next job will be to find out how to express this sigma Xx, or how to find out this sigma Sx in terms of the given load. So to express the sigma Xx in terms of the given load, what we'll do is we will refer back to the formula that we had derived in the previous during our previous lectures on unsymmetrical bending, with the special consideration that the kind of loading that we have will only contribute to mz. So going to the next page, we'll express the sigma Xx So we note that that we already know this. The sigma xx will be mz yiy minus z iyz. Divided by iyz square minus iyiz. Please note that this formula is only a part of the general formula for sigma xx that we had derived in the chapter on unsymmetrical bending, and I will provide the link for that lecture down below. Another important point is that here we have very much the expression for iyz present, because even though the y-axis and the z-axis are passing through the centroid, they are not necessarily the principal axis. So it is very much possible that iyz is not equal to 0. What this formula is not showing is the contribution from my, because the kind of loading that we have considered, that is not going to contribute to the my. Okay, so if we go back to the previous page, we see that we don't require the sigma xx directly, rather we need the derivative of sigma xx with respect to x here. So referring to this particular part, so what we really need is this thing. Therefore sigma xx derived with respect to x is going to give me all these things will remain as it is, but the mz, that will have a derivative with respect to x. Okay, but we know from our previous studies that the shear force will be related to the bending moment through this formula, so that if we quickly refer to the previous page, then the sigma sx will ultimately be expressed in terms of the shear force. So if we just substitute the expression for sigma for the del sigma xx del x, what we are going to obtain is sigma sx is equal to minus 0 to s del sigma xx del x ds so that is going to be equal to integration 0 to s vy. You note that this minus and this minus will cancel each other, and ultimately I will have this expression. Okay, now note very quickly that the iy, the iyz and the iz, they are characteristic, they are like the geometrical characteristics of the entire cross section, and they are like constants for any given cross section. So it really does not it is not necessary for us to keep them within this integration with respect integration from 0 to s. Furthermore, at a particular location, along the longitudinal axis of the beam, the Vy is having a particular value. It is not changing its value along the cross section. So what I mean to say is, if we go back to this diagram, the Vy will be as a result of the entire distribution of shear stresses here in the vertical direction. So if we are considering a particular length from this end, so if you're considering this particular length, so this the Vy there, the shear force along the vertical direction, that will be a given constant. In fact, for this particular problem, along the entire length, the Vy will be a constant, and that will be equal to the value that will be equal in magnitude to this externally applied force. If we have a more complicated distribution of transverse forces, then the shear force distribution will also change along the length. But we understand that, most importantly, that if we keep on changing the value of S from 0 to any generic S, the value of the shear force is not going to change. So that is also going to come out of the integration with respect to S. So let's recap. Vy can come out of the integration, the Iy can come out of the integration, the Iyz can come out of the integration, the Iz can come out of the integration. So you see, the entire denominator here can come out of the integration. This part can, this one and this one individually can. What cannot come out of the integration is this y and z. So what can you do about it? Well, we can kind of simplify this formula a little bit. So what we'll do is, we'll go to the next page and try to take out the things which we can out of this integration. Okay. So just to repeat what we had written earlier, so sigma Sx is equal to Vy y Iy minus z Iyz divided by Iyz square minus Iy Iz ds integration from 0 to s, and that will be equal to Vy divided by Iyz square minus Iy Iz. So Iy comes out, but the y stays inside. Integration from 0 to s minus Iyz integration from 0 to s z ds. So what have we gained by doing this? Well, you see, written like this, it is not of much use to us. But if we do a little trick of multiplying this integrations by the thickness, then we can get something really useful. So what I'm saying is, in each of these integrations, instead of just the ds, which depicts the length along the cross section, along the thin wall cross section, suppose we multiply this ds by the thickness, then the TDS would be representing an elemental area of the cross section. Similarly, if we multiply this ds by t, then it will be representing an elemental area. So what I mean by the elemental area will be clear if I refer back to this picture. So you understand that this is ds, this part is ds, the length of this is ds, but multiplied by the thickness across this, so that is T, that becomes the elemental area. So that's what I mean. So if I carry out that step, I have to note that since I'm multiplying throughout by T, I also have to divide throughout by T. So what I have is this thing. So maybe I can write that in a different fashion. So this is better, YTDS. It's the same thing, but I like this better. So this is IYZ, integration 0 to S, Z, TDS. Okay. So now the last thing that we have to note is interesting. The benefit of having written these integrations in terms of the elemental area is that we can immediately note that because this TDS is the elemental area multiplied by the Y, this basically represents the first moment of area about the Z axis. This one represents, so since this is the elemental area and Z is the distance from the Y axis, so this represents the first moment of area about the Y axis. So if we represent the first moments of area by the capital letter Q, then what we'll have is Vy that's IYIZ, whole thing multiplied by T in the denominator, and in the numerator I have IY multiplied by QZ, which is the first moment of area about the Z axis, minus IYZ multiplied by the first moment of area about the Y axis. And one last important thing is that for this particular case that we are considering, the Vy is nothing but minus of P. So you see what we have achieved. We have managed to write our expression for the sigma Sx, which again we note is equal to the sigma Xx XS in terms of the given load, which is P. So let me write that down by going back to the page here. So this is P, the magnitude of this externally applied force is P. So we have managed to write the shear stress in terms of P, in terms of the second moments of area, in terms of the thickness, in terms of the second moment of area, and here the first moments of area. So you see, overall we have managed to write down the expression of the shear stresses in terms of the given load. Now, does this mean that because we are developing a way to find out the shear center, does it depend on the given transverse load? Certainly not, because you see, although we have done a lot of we have gone through a lot of steps, but in terms of the means to find out the shear center, we have only done half. The other half, the next important step, is to actually make an account of the shear or the contribution from this shear stress to the torsional moment, and to equate that to the externally applied uh, torsional moment. So you note that if we take the torsional moment of this sigma xs contribution about any axis, this p is going to be present there, and if I balance this against the torsional moment which is actually contributed by the given applied load, uh, which is p itself, so from that balance this p is going to cancel out with that p. So the idea is like this. So if we go to the next page, so it may seem a little bit daunting that after doing so much we have only done half, but in reality we have done a lot. So so in an actual problem, what we have to do is calculate the torsional moment contributed by sigma xx, which is equal to sigma sx, and for which we have already found out the expression and equate it to the torsional moment contributed by the given transverse load P. So on the left hand side, we'll have the contribution from sigma xs, which is equal to sigma sx, and this thing will involve the p, because as we have seen in the previous page, the expression for sigma sx, it involves this p. And on the right hand side, what we are going to have is the torsional moment contributed by the given transverse load. And what is that value? So if we look back at this diagram, we can clearly see that the torsional moment which is contributed by the p about this x-axis is nothing but p times e. So this right hand side is nothing but p times e. So you see on the left hand side we'll have some expression which will involve the p in the numerator, and on the right hand side also we'll have some expression which will have p in the numerator. So this p on the right hand side and this p on the left hand side will cancel each other, and ultimately we'll have an expression for this e. So as we had mentioned earlier, this e will be depicting the distance of the shear center from the x-axis, and this location of the shear center is very much going to be independent from the given transverse load, which is P. Okay, so let's write that down. So what we have written here is that ultimately P will cancel from both LHS and RHS, and the E, the location of the shear center, will be independent of P. Okay, so with this we have kind of finished the theory part for the shear center. The ideas will be clear when you do some problems of finding the shear center. Okay, thank you.